previous few lectures, we have talked about individual aspects of I/O subsystem, talked about peripherals and the buses which interconnect them. We also have given some thought to how software looks at the whole operation. Today, we will look at the overall system design issues, and primarily the discussion will be in the form of examples, where we will see that given certain building blocks and certain requirements, how we put them together to achieve certain performance objectives. So, when you are designing the system, you have to keep performance in mind, and as we discussed earlier, the performance could focus on the latency aspect or the throughput aspects, or a combination of these. The latency is important in terms of achieving certain response time. So, when some event occurs outside, the system has to respond, and the response of I/O subsystem is very important in that case. So, you have data which moves from external world into the system, it gets processed, and then maybe some response comes back. So, as the data moves through various stages, all the delays get added up. The delay may be in terms of the rate at which the data gets generated at the peripheral, the way it crosses through controllers, buses and adapters, and finally, it goes through processing and follows a somewhat similar path. On the other hand, there is a throughput issue, where essentially the whole thing may act like a pipeline, and the slowest link in the whole system would basically dictate the throughput. So, as far as throughput is concerned, it is comparatively easier, at least if you have to find the average. So, you can imagine a steady state with data flowing, and if you understand the capability at each stage, about at what rate the data can flow, then you can get a reasonable estimate of the throughput. But latency could often be a more complicated issue. For example, the delay a block of data encounters going through, for example, a bus would also depend upon how much the load is being carried on the bus. So, you need to look at complex interaction between various pieces of information which flow through various components of the system, and at times analysis may not be very easy, and the last resort may be that you try to simulate the entire behavior and then see in a very accurate manner what kind of latencies you can obtain. So, in the example we will consider today, we will focus more on the throughput aspects. So, we will imagine steady state flow of data, and like fluid flowing through various pipes, we will try to see what is the throughput, what is the rate at which data can flow, and that will give us an idea of throughput. So, first example we will consider is one where there is an application where huge amount of data has to be read from various disks. So, or it could be the reverse, that there is lots of data which have to be stored on the disk. So, functionally it is a very simple application, that you have a processor, memory and lots of disks. So, we want to attain certain, we want to maximize our throughput, that is as much data we can pull out of the disks for a given capacity of processor, memory, bus and other component system, we will try to achieve that. So, the architecture you see here has a processor memory bus, on which a certain number of adapters, bus adapters are hooked, each provides an I/O bus. So, in this case we consider SCSI 2 I/O bus, which is supporting multiple disks. Okay. So, each can have one or more disks, and the disks read the data, send the blocks which traverse through this bus, go through the adapter and ultimately go to the memory. The processor, for each block of data which gets read, there is some certain amount of processing involved from both point of view, to organize the IO as well as to act upon the data. So, let us look at some numerical parameters associated with various components. The processor has an instruction execution rate of 300 million instructions per second. Okay. So, that quantifies the capacity of processor to perform certain task. The bus which connects processor and memory is capable of handling a throughput of 100 megabytes per second. Okay. So, data which comes from various sources is considered on this bus, and when it is being deposited in the memory, one has to keep in mind that there is a certain throughput limit here. And how we arrive at bus throughput limit, we have discussed. It depends upon the protocol, the size of block which is being transferred, and so on. So, suppose that analysis was carried out separately, and one comes up with a figure of 100 megabytes per second. Then these SCSI2 buses, okay, each has a capacity of 20 megabytes per second. So, these buses are carrying the data from the disk towards the memory. Each SCSI controller is capable of handling up to 7 disk drives. Okay. And each disk drive requires 10 milliseconds to access, that is seek time plus rotational latency plus controller delay, and then rate at which data gets read out, data gets transferred is 5 megabytes per second. Okay. Now, let us also define what each IO operation is. Each IO operation involves 64 kilobytes of data to be read from the disk. So, let us say it has to be read from some contiguous area on the disk from a single track, but every time you read a block of data, it may be a different track. So, every time we have to incur 10 milliseconds of delay before we start reading the next block, and once we have incurred the 10 milliseconds delay, then 64 kilobytes will come continuously at the rate of 5 megabytes per second. Now, as far as the SCSI bus is concerned, when one disk is busy in seeking or it is rotating to get to the position, other disk could be transferring the data. So, seeking and transfer among different disks could overlap. Okay. Now, each IO operation of 64 kilobytes transfer requires some work on the part of the processor. So, 100,000 instructions are executed by the user program, and 50,000 instructions are executed by operating system. So, imagine that each transfer takes place using DMA process, which means that the processor will initially set up the process, it will instruct the DMA controller. We are not showing. So, let us say that all that SCSI control and DMA control is lumped within the bus adapters. So, it has to initially instruct the DMA controller to read from a particular track and particular sector from a particular disk, and it also supplies the address in the memory where things have to be deposited. So, that is the initiation part, and when the transfer is over, it needs to be informed with the help of an interrupt. So, again some instructions get executed. So, on the whole OS goes through 50,000 instructions all put together, beginning and end, and the data is processed by the CPU. It requires 100k instructions of the user program. So, now what is it we need to do? What is the problem? Problem is to find out what is the maximum input output rate that this system can sustain. So, the fixed components here are, there is one single processor, one single memory and a single processor memory bus. The flexibility is in terms of putting as many disks as you can gainfully put in the system, and depending upon the number of disks you have, you will require certain number of SCSI buses and corresponding controllers. So, the problem involves first finding out what is the maximum IO rate, that means how many IO operations as defined here can be carried out, okay, at what rate can you do those, and to achieve that how many disks and SCSI controllers are required. Okay. So, now to solve this, first let us analyze what are the limits of individual components, and the limit will come from the fixed component, that is the processor and the memory and corresponding bus. So, the processor has to execute 100 plus 50, that is 150,000 instructions per IO block, and this execution happens at the rate of 300 million instructions per second. So, maximum IO rate as far as processor is concerned is 300 million divided by 150 k. Okay. So, many IO operations per second is possible. So, this turns out to be 2000 IO operations per second. So, if rest of system was capable of matching this rate, the processor is ready to do 2000 operations as defined here per second. The next object is processor memory bus. So, what is the limit as far as this is concerned? The bus has a bandwidth of 100 megabytes per second. Each IO block, it may come from some disk and some SCSI controller, ultimately it will land up on the same bus, and the bus will have to carry out transfer of 64 kilobytes. So, now from these two figures you can figure out 100 million bytes per second is the capability, 64 k bytes you want to transfer. So, basically you get 1562 IO operations per second. Now, out of these two figures, 2000 of CPU and 1562 of PM bus, obviously this is smaller figure and therefore, that is the bottleneck. So, processor has certain spare capacity and this will dictate the rate. So, our first answer is that overall maximum IO rate is 1562 IO operations per second. Now, the question is how do we achieve this? How many disks we need to put to do this? So, let us look at one disk at a time. The seek plus rotational latency is 10 milliseconds, and with 5 megabytes per second of transfer rate and 64 kilobytes of block size, the transfer time would be 64 kilobytes divided by 5 megabytes per second, comes out to be 12.8 milliseconds. Okay. So, now for each IO operation, basically disk has to spend 10 milliseconds followed by 12.8 milliseconds, and therefore, on the whole each disk when it gets involved in IO is busy for the sum of these two figures, that is 10 milliseconds latency plus 12.8 milliseconds transfer time, or total of 22.8 milliseconds. So, if disk was to be continuously asked to seek and then transfer, seek and transfer, the rate at which this can churn out blocks is a reciprocal of 22.8 milliseconds or 43.9 IO operations per second. Okay. So, the throughput which actually disk is sustaining is 64 kilobytes have been generated in a time of 22.8 milliseconds. So, it is although transfer rate was 5 megabytes per second, effectively we are getting 2.8 megabyte per second is the demand each disk is placing on the SCSI controller. So, that much of data it is pumping on the SCSI bus, and SCSI bus will concentrate from various disks and send further. So, now to begin with, let us we want to use this figure to get the number of disks. We have seen that maximum IO rate of the system is 1562 IO operations, and IO rate of the hard disk drive is 43.9. So, the total number of disk drives which you require to saturate the PM bus is the ratio of these two, 1562 divided by 43.9. So, rounded off to integer, you get 36 disks. Now, the question is of how do you distribute these 36 disks to various SCSI controllers. The number of controllers you require at least is 36 by 7 ceiling of that, because each controller is able to at most sustain, at most control 7 of these. So, now this limit of 7 is from the point of view of its addressing capability. Okay. We also have to check whether the data generated by these disks will be handled by the bus of the SCSI controller. So, the number of controller by this ratio comes out to be 6, okay. And accordingly the number of drives which each controller is assigned, if you distribute them uniformly, it comes out to be 6. So, 36 drives are grouped into 6 groups, and each controller will see a throughput of 6 times 2.8. Okay. We have seen earlier that each disk is actually pumping data at the rate of 2.8 megabytes per second. So, which is 16.8, and therefore, this is within the limit of 20 megabytes of the SCSI bus. So, therefore, our answer which we have got here is fine, that you need 36 disks and 6 controllers. So, that was one exercise where the parameters were number of disks and number of controllers, and we were able to analyze and decide how this is figured out. Yeah, before I go to next example, is there any question? So, they are very simple calculations, very simple rules, there are no complicated formula. You just have to see how things are put together, and there is a lot of actually common sense which is behind this. Once you understand the operation of how things are happening, rest is very straightforward. Okay, the second problem we take is again a design problem. What we are trying to do is we want to design a multifunctional unit, particularly something which can do photocopy and send and receive faxes. And the way we want to do this is we take a low cost scanner, a low cost printer and a modem, and connect them through some inexpensive processor and suitable memory. Okay. So, put these peripheral devices together, and we have certain performance objectives. I will come to that in a moment. So, functionally these will take care of this. That is, you can scan a document and fax. You can take an incoming fax and print it. You can also scan and print, so which is effectively like a photocopy operation. So, this is what I already said. Modem plus printer function as fax receiver, scanner plus modem function as a fax sender, and scanner plus printer act as photocopier. So, of course, in between you have a processor and memory sitting in the background. Now, we also assume for our further calculation that every photocopy operation may require certain number of copies, that is you scan and print a couple of copies. Let us say the average number of copies you print for every document you scan is 3. Okay. Then there are certain operating requirements in what kind of scenario you want this to work. So, let us say there is a heavy fax load. So, continuously fax are coming and going, and we will work with the assumption that the telephone line to which this is connecting is continuously kept busy. So, let us say half the time it is okay, it is written here, incoming and outgoing faxes are balanced. That means, almost equal number of faxes come in and equal number has to be sent out, and each fax message is a single page. We do not want to worry about the complication of sending multiple pages. So, just imagine that each we are only dealing with A4 size pages. So, both printer and scanner have to work with that, and after satisfying the fax load, whatever is the spare capacity of scanner and printer is to be utilized for photocopying, and we want to get a feel of, we want to know how many maximum, at what rate we can do photocopying process. So, we want to find eventually the throughput for each type of operation. That means, what is the rate of fax messages that would be sustained, and what is the rate of photocopying that could be achieved. So, this is a block diagram of the whole system we have in mind. We want to make it low cost setup. So, there is a processor memory bus and a single I/O bus. Okay. So, there is a bus adapter sitting here, a scanner, printer, modem which hooks to a telephone line, and maybe we might need a disk drive. So, that is a question mark, although it does not come directly from the specification. So, we want to build it as a sort of dedicated system, and once it is designed and all assembled, we want it to be just doing this work as a fax machine plus a photocopier. So, whatever program is there could be possibly put in non-volatile memory, and you can, if disk is not required, we will not put that, it will save maybe little bit of money. So, of course, these I am ignoring the details that these devices will eventually perhaps connect to different type of port or a bus. For example, modem may go to serial port, these may connect to USB port, or printer may go to parallel port, and so on. So, we will ignore that last point detail and assume that there is a single bus from which eventually all these interfaces will be hooked up. So, now let us look at the building blocks which are available. So, something will be sort of fixed and somewhere there will be choice, and we will figure out what choices we make. So, let us say printer and scanner are available to us. We will take a low or medium resolution print machines, 300 DPI. We do not need a 600 or 1200 DPI. The page size, fixed page size has to be handled, and just to round it off, let us say it is 11 inch by 8 inch A4 size, and it can, both these can work in two modes. One mode is when you simply work with black and white. Okay. So, there are no gray levels, each pixel is either black or white. Okay. And in second mode you have 256 gray levels which you can represent with a byte. So, for fax purpose we will use mode 1, and for photocopy purpose we will use mode 2. Let us say the scanner works at the speed of 4 pages per minute and printer works at the speed of 8 pages per minute. Okay. Continuing with the building blocks, we have a modem available. We are not taking top of the line 56 kbps modem, we let us take 33 kilobits per second modem, and it also, let us say there is a 10% overhead, that is whatever data is to be sent, a few bits as part of the protocol has to be added by the modem, and let us say it is 10% extra data which gets added. There is a disk available which has a latency of 10 milliseconds and transfer time of 5 megabytes per second. We want to use again a low cost processor which is available in two options, 100 megahertz or 200 megahertz. So, it is not a gigahertz type of processor, and it is not pipelined, it has a CPI of 4, it does not have cache. So, directly accesses memory. The program which will be running on this to carry out this operation, fax requires certain encoding and decoding. Okay. So, you have the scanned image of the page that needs to be encoded in certain form before you send, and this encoding actually compresses the size of the data. Similarly, the fax which is received has to be decoded and put back into a pixel matrix. So, I think that number is mentioned later. So, we will assume that there is compression or decompression of factor of 10:1 which is happening. And this process of encoding or decoding involves 100 instructions per byte of raw data. So let us say you have scanned the image. If the image is 10 kilobytes, you will require 100 instructions to be executed per byte, or if it is 1 megabyte, accordingly. So the algorithm of encoding or decoding either way has to incur some computational load, which is spelled out here. Also, each IO operation, I am assuming a flat rate of 100k instructions per IO operation. So, for example, sending a fax would involve scanning and sending to the modem. So each has to be set up in a DMA manner, and I am assuming that each will require each will consume 100k instructions of the processor. And on the average, the program would have, let us say, 30% of the instructions which are of load store kind, which will make additional access to the memory. The memory is available in two sizes, 64 megabytes or 128 megabytes, and two speeds, 40 million words per second or 60 million words per second, and there is an appropriate synchronous bus which will connect it to the processor. The IO bus is to be used, there is no choice here, it is 10 megabytes per second. So, now with all this we can proceed and try to put things together, see what kind of rates we get, and what choices we made, what choices could be made for processor and memory. So let us first try to understand what information each page carries. We have seen that resolution of the page is 300 dpi, and with page size of 11 inches by 8 inches, we get total number of pixels as 11 into 8 into 300 into 300, which is 7.92 million. Okay. So, those many pixels are there. Now, depending upon the mode, whether it is black and white mode or a grayscale mode, you will require certain number of bits per pixel. So, mode 1 is 1 bit per pixel and mode 2 is 8 bits per pixel. So, you get for 7.92 megapixels, you get 7.92 megabytes or 0.99 megabytes. Okay. So, these are bits, we have converted to bytes. Now, the compression in fax encoding was 10:1. So, when you have to send or receive a page of these many megabytes, actually what goes on the fax line will be 1/10 of that. So, 0.099 megabytes. Okay. Okay. Now, memory and disk size, let us have a look into that. So, let us assume that the code or the software will take something less than 20 megabytes. So, 64 megabytes of memory will be adequate in the sense that we do not have to put 128. 64 megabyte will accommodate easily the program, and it can also buffer several pages which have been scanned or which are waiting for printing, okay, because each of these requires something like 8 megabytes. So, 64 megabyte gives us a reasonable cushion for accommodating a couple of scanned pages. And since everything can be accommodated in memory, we can eliminate the use of disk. We can have the memory itself as a non-volatile memory, or we could have a volatile memory augmented with the flash memory, because flash memory is slower. So, you will not like to execute program directly from flash. Instead of disk, you can put a flash memory. Okay. Now, let us go to the fax process. So, modem speed is 33 kilobits per second, or in terms of bytes, you can divide by 8 and get 4.125 kilobytes per second. And the compressed page or encoded page is 0.009 megabytes which is same as 99 kilobytes, and with 10% of overhead we can find out transmission or reception time, right. So, 99 multiplied by 1.1 because of its overhead divided by the kilobytes per second rate, we get 26.4 seconds. So, each page takes this much time to be sent or to be received. Okay. Plus, now since this happens over telephone line, there is time taken to establish a call. Okay. Either there is an incoming call and modem will respond to that established connection, or when it is to be sent, number would be dialed and connection would be established. So, let us say 20 seconds either way get used up for this purpose, for establishing a call. So, the two put together 26.4 and 20 is total time which is actually taken for which the modem and line are busy is 46.4 seconds, and therefore, fax rate, the rate at which you can be handling faxes incoming and outgoing all together is reciprocal of this, which is 0.022 per second, or you can have a more convenient figure in per minute, 1.32 per minute. So, basically this is one of the responses. This setup here the things are actually limited more by the modem speed, okay, the rate at which you can send fax, and it is not so much influenced by the other components which are in the picture. So, this is the rate which modem can sustain, and rest of the system has to actually work with this. Now, let us turn our attention to scanner and printer. So, scanning rate is 4 ppm, or in terms of pages per second it is 0.067. So, many pages per second. The outgoing fax rate 0.022 we divide into 0.011 incoming and 0.011 outgoing. So, now the scanner has to match the outgoing faxes, and therefore, if so many faxes are going out, so many pages have to be scanned, all right. So, the capacity of scanner available for photocopying is the difference of these two. Okay. It has total capacity of 0.067. If you were to continuously scan pages, so many pages per second could be scanned, and out of that so many will be faxed out, rest could be used for photocopying purpose. On the other hand, printing rate is 8 ppm or 0.133 pps pages per second, incoming fax rate is 0.011. So, capacity available for photocopying is 0.122 pages per second. Now, so these are the spare capacity, and how many photocopy operations we can do. Since if you recall, I mentioned that for each page you scan, you will print on the average 3 copies. So, printer has a slightly higher load, and this figure is certainly less than 3 times that. So, basically printer would dictate the photocopying rate, and we say that we will be able to churn out so many photocopy pages per second, and that means 1/3 of that we need to scan on the average. So, 0.0407 pages per second are scanned, and 0.122 pages per second are printed in the photocopy process. Okay. Now, we go to the I/O bus requirement. So, we have looked at each peripheral. We have looked at the modem, the scanner, and the printer. We have gotten away with the disk. Okay. So, now I/O bus has to basically sustain the throughput which is being generated by these. So, when you are receiving a fax, you have data coming from modem and it goes to the memory. Okay. It passes through the I/O bus, and similarly for outgoing fax, it comes from memory and goes to the modem. So, it passes through the I/O bus. Similarly, from memory to printer or scanner to memory will happen at this rate. For each page per page is 0.099 megabytes per page is the modem traffic, and 0.99 megabytes per page is the printer scanner traffic. So the data rate which the IO bus sees for the fax operation is 0.022 faxes per second multiplied by so that means so many pages per second, and these many megabytes per page. So the product gives you 0.024 megabytes per second. So that is the demand placed on the IO bus by the faxing operation. For photocopy operation, there is a traffic between memory to printer or scanner to memory, which is 7.92 megabytes per page. Okay. And the rate at which we are doing photocopy, we are scanning 0.0407 pages per second, that sends out this much of data, and 0.122 pages per second we are printing. So that again demands that much data. So sum of this is 1.289 megabytes per second. Okay. So that is the total demand which is placed by photocopying operation when it is running to its peak on the IO bus. So sum of these two 0.024 and 1.289 megabytes per second is 1.313 megabytes per second is the total IO demand, and the bus which has been provided to us is 10 megabytes per second. So we are very comfortable with that and we can accept that solution. Now let us see how the processor is doing. The instruction which it needs to execute per fax message is I mentioned that there are 100 instructions per byte. Okay. So 0.99 megabytes is the page data. So this product gives you the number of instructions which will be required for either encoding or decoding a page. Okay. And each fax in or fax out involves two operations. So either reading from the modem or writing to the modem, and on the other hand either scanning or printing. So each will require 100k instructions. So total of instructions which have to be executed is these many for either encoding or decoding, these many for either sending or receiving. So this turns out to be, actually this is a very small component, as you can see. So bulk of the computation power is going in encoding or decoding. The IO part is much smaller. So this is 99.2 million instructions per fax incoming or outgoing. Okay. The instructions executed per photocopy. Now I have made a mistake here, it should have been 4. So on the average you are reading, you are doing one scan and you are doing 3 prints. So it should have been 4 here. So each requires 100k instructions. So total 0.4 m. Okay. The total instructions throughput required is this much plus 0.4 sorry this into the fax rate and this into the scan rate. So together you will get 2.19. This in any case is a small factor, it will make minor difference here. So let us not worry about that. The total instruction rate required on the part of processor is 2.19 million instructions per second. And we talked of 100 megahertz or 200 megahertz CPU with 4 CPI. So basically 100 megahertz CPU will require, we will actually deliver 25 MIPS, which is very comfortable to handle that. Okay. So we do not need to go for 200 megahertz processor, we can work with 100 megahertz processor. In fact, if there was a 50 megahertz version available at a cheaper rate, we would have picked that. So in any case, out of the choice given, this is quite adequate. The memory bandwidth, now we are not utilizing the processor to the full capacity, but suppose after having seen that processor is underutilized, maybe we might put in some other tasks on that. Suppose processor was to run at full capacity, it was not to stall for lack of no work, for lack of work. 25 MIPS would require 25 million instruction words to be fetched per second. Okay. And load store, we noticed earlier, was 30% of the instructions are of load store type. So, additional demand would be 0.3 into 25 or 7.5 million words per second. So this is the traffic which processor will generate for the memory. Okay. 25 million words per second and 7.5 million words per second, instruction traffic and data traffic, load store traffic. The IO traffic is also showing up on the memory bus. So, which is very small, 1.313 megabytes per second. So, all put together, the memory bandwidth needs to be capable of handling this 25 plus 7.5 plus 1.314 divided by 4 to get million words. This was million bytes actually. So, that is only 32.9 million words per second. And so, we can pick up the memory which has out of the 40 and 62 possibilities which were shown, we can pick up the one which has 40 million words per second capability. So, that is adequate for our purpose. So, so basically as a end result, you can see that we have we can get certain throughput rate for fax and photocopy operation, and we are able to sustain that with the simpler of the processor and slower of the memories. So, that is all as far as this example is concerned. If you have any questions, I hope these calculations are fairly straightforward. You only need to proceed in certain manner, and there is no fixed rule or procedure to solve such problems. Each problem may be of its own kind, and we all along we should understand what are the assumptions we are making in all this analysis. We are assuming that everything is in a steady state. Okay. So, there are no accumulations of data, or nothing is getting starved for data. So, there are no congestions or no starving. All traffic, all data traffic or instruction traffic is flowing smoothly, and there is a steady state. So, if you have multiple buses converging to one bus, you simply add the traffic coming out of multiple devices which come on the same bus. So, we have not analyzed here the delays, that is once a fax comes, how long it takes to print. Okay. So, that was a latency issue, or from the time you press a scan button, okay, how long it takes to get 3 copies printed out. So, that we have not analyzed, that is somewhat more complicated, and often you need to use you may not be able to simply add the delays, because as you are these operations are all interleaved. As you are receiving and sending faxes, photocopying is taking place. Okay. So, these are interleaved, and there may be sometime queuing delays. Okay. So, which we have not worried about in bandwidth calculations, but when you look at the latency, you would need to for example, a page has been scanned and it needs to be printed. So, how much is the delay between the two? When will the processor execute those instructions required? When will the bus be free? When will the printer be free? Okay. So, that analysis may require tools like queuing theory, for example, or sometime even if that is not adequate, you would need to actually simulate the whole scenario and then study how much latency is involved. Okay, so that's all for the moment. Any questions you have?
So in design example 1, the maximum capacity of disk is 5 MB per second.
Yeah, that is the rate at which disk is able to transfer data once you reach the appropriate point.
So sir, can't it happen that all the disk on a single controller are transferring data, that is none is seeking the data? So that will amount to 30 MB per second on each IO SCU.
Yeah. So that's where things will get buffered in the controller. Okay. So let's say what you're saying is very realistic, and it's going to happen. It may not be simultaneous, but let's say one disk has started transferring. Maybe it is halfway through. Another disk is ready. Okay. So now what will happen? It may be there will be some buffering at the disk end. Okay. There will be buffering at the controller end, right. So also we would need to understand how actually the two streams of data get put on the bus. Do you allow them to be interleaved or not? So let's say they are not interleaved. Okay. So the data which is taking 12.8 milliseconds to come out of the, as it is coming out of the disk is active for 12.8 milliseconds. Okay. But the rate at which it goes on the SCSI bus is 20 megabytes per second. So let us say there is no interleaving of the blocks from two different sources, and therefore the SCSI bus will be occupied with this much of data for how much time? For 64 kilobits of data over let us see, it will be 1/4 of that actually. So since this is 5 megabytes per second, so some 3.2 milliseconds. So basically what will happen is that if you are not allowing interleaving, it will be better to buffer this 64 kilobytes somewhere, okay, either at the disk controller end or at the SCSI controller end, and then put it for 3.2 milliseconds on the bus, right. Let me try to show you timing. So one disk, let us say, spent 12.8 milliseconds, and let us imagine that this data is going to some buffer, and then over a period of 3.2 milliseconds it is occupying the SCSI bus, and over a shorter period, how much was the memory bus? I think 100 megabytes. Yeah. So 1/5 of that. So a fraction of milliseconds it will be present on the processor memory bus. Now in between here, although I am showing it contiguously, but there could be gap here. So in actual practice we should be open to have situation like this: 12.8, then some gap, somewhere down the line 3.2 millisecond it spends on the SCSI bus, somewhere later with I do not know how much break, it will spend 3.2 by 5 so many milliseconds on the PM bus. So now each transaction, you can imagine, has these three parts, and you have another one such thing coming from a different disk. So it may be its 12.8 was happening here, okay, and its 3.2 may get just placed after that. So you have basically these streams coming from different disks, they get buffered, and one after another they will be placed on the SCSI bus. Similarly, the adapter which is sitting on the main, when it is put on the processor memory bus, again they will be sequentialized, put one after another. So, let us say it gives a thin burst on PM bus. So, suitable buffering at various ends will take care of this. Does it answer your question? Any other question? Okay, thank you.